we are talking about the similar figures. Similar figures means which have the same shape and have the different size. Shape means what depends upon the angles. So it means angles of the both shapes are same. Size means that they should have a constant ratio between their respective sides. I will explain it further. So when the two shapes have the same size, same shape and the different size, then the figures are said to be called similar figures. Suppose there's a triangle ABC and there's another triangle DEF. So there are three theorems for these similar figures. First part, AB is represented by the opposite vertex C. This is opposite vertex A and this is opposite vertex B. This DEF, the opposite vertex is F, this is opposite vertex is D, and this opposite vertex is E. The first property is there. If C over F is equal to A over D is equal to B over E, and that is equal to a constant K, then the two figures are said to be called similar figures. The second property is if C over F is equal to A over D, which is equal to a constant K value there, provided this angle B is equal to this angle E there. The including angle is same. So angle B is equal to angle E. Then the two figures are called to be similar figures. And the third property is that if angle A is equal to angle D, angle B is equal to angle E, or angle C is equal to angle F, then again the two figures are called to be similar. And this is the sign for the similar figures. ABC similar sign with the triangle DEF. So this is the three theorems for the similar figures for the triangles. That first part, that they should have the constant ratio between all the sides is same. Second, two sides have a constant ratio with the including angle is same, and any two of the angles are same, then the figures are called to be similar figures. So this is the three theorems for the similar figures. Now, for the area and the volume of these figures. Let's say the area of this one is A1 and this is the area of A2. So A1 over A2, which is equal to K there, and it should be equal to square of these two values there. Now we will prove it that how they are similar and how the proof of this one is supposed to be. Let's say A1, this is the height h of this figure, and this is the height capital H of this figure. Since we know that the area of this triangle ABC is equal to half base into height. So half base is their C and height is their H. So area of this triangle ABC is equal to half CH. For this triangle DEF, it is the same formula will be used there. Half, base is there F, and height is there capital H. Now, we will define one by one with the part of this. Since if we look at this first property, that F C over F is equal to K, then C is equal to KF. Now we put C is equal to KF in this part. So area of this triangle ABC is equal to half into KF into H. And similarly, we can find out this H value there because they have the constant ratio. So H over capital H is also equal to K. So H is equal to K times of H. So we can write it here, KH there. So this figure will become equivalent to half K square F H. And this can be written as, for this area of this triangle ABC is equal to K square into half F into H. But half into F into H is basically the area of this triangle. So triangle ABC over triangle is equal to K square of this triangle DEF, or triangle ABC over area of this triangle DEF is basically equal to K square. ABC is represented by A1, DEF is represented by A2. So that is the theorem, we have proved it there, that when the two figures are similar to each other, then the area ratio is the square of the ratio between their respective sides. And now you will prove it for the volume of this figure. For this volume now, V1 over V2 is equal to KQ. That means the ratio between their volumes is the cube of the ratio between their respective sides. Let's prove it. Let's say there is a cuboid with length small l, with width small b, and this height small h. There is another cube which is having a ratio between them is constant, where this is the capital length, this is the capital width, breadth, and this is the height of that. So now we have to prove it that they have the cubic ratios between the respective sides. Since small l over capital L is equal to small breadth over capital B is equal to small height over capital height, and that is equal to constant ratio K. This is the first property, that they should be first similar to each other. That the length ratio is same as the breadth ratio, as same as the height ratio. Now, let's say the volume of this one is V1 and volume of this one is V2. Then V1 is the length into breadth into height. So we can write this thing as V1 is equal to length into breadth into height. Let's say it is question number 1. Then the volume for V2 is length into breadth into height. Let's say that is question number 2. But we know from this equation number 1 that length ratios is the same as breadth ratio is the same as for the height ratio. So if we pick length, then it should be equal to K times of length. breadth should be equal to k times of b, and height should be equal to k times of h. Now v1 is equal to length into breadth into height, so it should be kl into kb into kh. So this is basically equal to k cube into length into breadth into height. This is v1. So we know one thing, that length into breadth into height is the volume v2. So v1 is equal to k cube into v2. Or if we shift it toward this side, v1 over v2 is equal to k cube. So we have proved it here that when the two figures are similar, then the volume ratio is the cubic ratio between their respective sides. Keep this thing in your mind that they should have a respective sides constant there. That the ratio between their length should be the same as the ratio between their width, should be the same as the ratio between their heights. So this is the proof of this, that volume ratios is the cubic ratios between their respective sides, and area ratio is the square of the ratio between their respective sides. Now we will prove it with the different problems in this geometry in the SAT one in other test.